Okay, as I mentioned at the end of the previous video, here we do some examples of applying the second derivative test to determine local max, local min, or the saddle point of a function of two variables. So let us start with an example that for which we found the critical point. So let me repeat that example, but this time we want to determine, or we want to find local mean, local max, and saddle points, if any. So let f of x be minus x squared minus y squared minus 6x plus 8y. Part one, we want to find critical points. In the previous video for this function, we found the only critical point, and that was the point -3 and 4. We did this in the previous video for the same function. Now, part two, we use the second derivative test to use the second derivative test. We use the second derivative test to determine the whether we have local max, local min, or saddle point. So as you know, we should find d of x and y, which is the second derivative purely with respect to x times the second derivative purely with respect to y minus the mixed derivative, the mixed second derivative squared. You can easily see that the second derivative with respect to x, if you do it correctly, the given function, the function on the top, if you differentiate with respect to x twice, meaning finding the second derivative with respect to x, purely with respect to x, you will find this is going to be -2. We don't even see x or y in that. In some cases, x and y might remain, but here after finding the second derivative, we just get a constant value -2. The same thing with this. If you find the second derivative, you'll have -2, then minus the mixed derivative with respect to x and y. If you differentiate with respect to x first and then with respect to y, you will get a 0. So -2 times -2 minus 0 squared. -2 times -2 is 4. 4 minus 0 is 4. So in fact, d of x and y, no matter what x and y are, is going to be 4. In particular, I want to know that at this critical point, what is d? So d of every x and y is 4, so d of -3 and 4 is also 4, which is positive. According to the second derivative test, if d is positive and here the second derivative with respect to x at -3 and 4 is -2, which is negative, If d is positive at the critical point, and if d is positive at the critical point and second derivative with respect to x is negative, then we have a local maximum at -3 and 4. Therefore, f of x and y has a local maximum at -3 and 4. We have no local minimum, no saddle point, and the second derivative test was conclusive because it is inconclusive if that d at the critical point becomes 0, but d at -3 and 4 is 4. It's not 0, so the test is conclusive. Just a little correction up there. This was f of x and y, obviously. It was a function of two variables, so we had this. Please look at the second derivative test that we talked about in the previous video, that we had 4 possibilities, and in one case we had a local max, one case local min, one case it was saddle point, and if d at the critical point equals 0, the second derivative test is inconclusive. Now let's see another example. The second example, again, is a function of two variables. Let f of x and y is x to the 4 plus y to the 4 minus 4xy. First, I want to find part 1 critical points. So I should set the first derivative with respect to x equal to 0. On that function, the first derivative with respect to x is 4x cubed minus 4y. The first derivative with respect to y must be 0, which is 4y cubed minus 4x. So these both of these two should be equal to 0. So I come up with this system of equations. 4x cubed minus 4y is 0. 4y cubed minus 4x is 0. In each of these equations, 4 is in common. I can factor 4 out and divide both sides by 4. And since the other side is 0, 0 divided by 4 still remains 4. So the first equation is x cubed minus y and y cubed minus x. This is a kind of nonlinear system of equations that in more elementary courses, you have seen these kind of things. Like one way to solve this, from the first equation, I solve for y. So y is x cubed. Then I substitute this into the second equation. So using y equals x cubed and substitute into the second equation. So that y cubed minus x equals 0. I replace y by x cubed. X cubed cubed is x to the 9. X to the 9 minus x is 0. So x is in common. I can factor that out. X to the 8 minus 1 is 0. So one value for x is going to be x equals 0. If x to the 8 minus 1 is 0, since 8 is an even power, I get two values, 1 and minus 1. Now, how can I find the corresponding y? Like here, if I use this equation on the top, or in fact, excuse me, if I look at this y equals x cubed, when x is 0, the corresponding y is going to be 0 cubed, 0. When x is 1, the corresponding y is 1 cubed, y is also 1. And when x is minus 1, y is minus 1 cubed is minus 1. So we use the y equals x cubed to come up with these values of y corresponding to those x's. So in fact, we have three critical points. x0, y0, 1 point, 0, 0. The next point, 1, 1. And the last point, minus 1, minus 1. So the fact that y equals x cubed helped us to know that what is the corresponding y for every value of x. So we have three critical points. So I should apply the second derivative test to each of these 3 points to determine whether we have a local max, a local mean, or a saddle point at these 3 points. So in part 2, for the same example, use the second derivative test. Use the second derivative test to determine local max, local mean, or saddle point. Again, first of all, I need to find this function of x and y, which is the product of the second derivatives with respect to x and with respect to y. Minus the mixed second derivative squared. So look at the function here. If you find the second derivative with respect to x and deal with y as a constant, you will get 12x squared. So this is going to be 12x squared. Second derivative with respect to y. Again, you will get similarly 12y squared. It's the product of these two minus the mixed second derivative. So meaning that first we differentiate with respect to x, and then we differentiate with respect to y. It's very easy to see that it's going to be -4. So in fact, d of x and y is 12x squared times 12y squared, 144x squared y squared, minus 4 squared is 16, and then minus 16. Now I should see what happens at these 3 critical points. So first, let me check 0, 0. At 0, 0, d of 0, 0 is what? So x and y are 0, so 144, 0 squared is 0 squared minus 16. Obviously, this is just minus 16, which is negative, meaning that we have saddle point at 0, 0. At 0, 0, a saddle point. Now, at 1, 1, I should look at d of 1, 1. So it is 144 times 1 squared. 1 squared minus 16. Obviously, this number 128 is positive. So d at 1 and 1 is positive. Now I should look at the second derivative with respect to x at 1 and 1. At 1 and 1, obviously, the second derivative with respect to x was 12x squared. At 1 and 1 becomes 12. It's still positive. So it is 12 positive. So both are positive. D is positive. The second derivative purely with respect to x positive. According to second derivative test, we can say that at, excuse me, at 1, 1, we have a local minimum. At -1 and -1, we have a very similar situation, and d of -1 and -1. I'm sure that you can do it on your own, and you get, again, 128 as well. And the second derivative with respect to x at -1 at -1 is, again, 12, is positive. So both d and the second derivative purely with respect to x are positive. So at -1 and -1, we have another local minimum. Obviously, we checked all the critical points, and we have no local maximum. So 2 local minimum and 1 saddle point. The test was conclusive because at every point we were able to determine the situation. So at every critical point, the test was conclusive. Okay, let's see another example. Let f of x and y be equal to 4x e to the power of y minus 4e to the power of x. Part 1, we want to find critical points. So I find the first derivative with respect to x and with respect to y and set them equal to 0 to find the critical points. With respect to x, this is going to be 4EY minus 4EX. So I deal with x as a variable and y as a constant. And with respect to y, the derivative is just 4x e to the y. So I set these to equal to 0. 4e to the y minus 4e to the x is 0. 4x e to the y is 0. Of course, I can factor 4 out in the first equation and divide both sides by 4. And since the other side is 0, 0 divided by 4 is just 0. So e to the y minus e to the x is 0. I can do the same thing with the second equation and divide both sides by 4. Now, in the second equation, I see that x times e to the y is 0. You know that e to the y can never be 0. So the only possibility is x is 0. So from here, I can conclude that x is 0. Now I go back to the first equation. From the first equation, e to the y minus e to the x is 0. So this tells me that e to the y equals e to the x. And since exponential function, as you know from calculus 1, as you might remember, the graph is an increasing function, and it's a one-to-one function. So if e to the y wants to be equal to e to the x, that means x is equal to y. So having these together tells me that the only possibility for the solution is x is 0 and y is 0. So from the second equation, I got x is 0. From the first equation, I got x equals y. So y must be 0 as well. So the only critical point that we have here is 0, 0, just one critical point. Now I want to use the second derivative test. Use the second derivative test to determine whether we have local max, local min, or saddle point. Since it's only one critical point, only one of those happens. So again, I need to form this function of x and y that is defined by second derivative with respect to x, second derivative with respect to y, minus second mixed derivative squared. This second derivative with respect to x, you can see easily that it is minus 4e to the x. With respect to y, this second derivative is 4x e to the y. The mixed second derivative, you can easily see that this is going to be 4e to the y. So let's see write it in a better way. So d of x and y is the product of these two. So minus 4 times minus 4 minus 16, x, e to the x, e to the y. And minus 4 squared is 16, e to the power of y squared. E to the power of y all squared, as you know from basic algebra, it's e to the power of 2y. So that's the d that we need to calculate as at 0, 0. So let's see what is d at 0, 0, the only critical point that we have. X is 0, y is 0. Since there is x here and x is 0, makes this product, the first term 0, then minus 16. E to the power of that y is also 0. E 2 times 0 is 0, e to the 0. And e to the 0 is 1, so this is just minus 16. Which is negative. And once d is at the critical point is negative, it says that according to the second derivative test, at 0, 0, we have a saddle point. So we have no local max, no local min in this example, only one saddle point. And obviously, the second derivative test is conclusive because it was able to determine what the only critical point is one of those three, like local min, local max, or saddle point, in this case, saddle point. If d at any point, at any critical point turns out to be equal to 0, then it's inconclusive. But here d is not 0, so it is conclusive.